Whenever someone's learning data science or getting introduced to it, there's often the inevitable question when you get to machine learning of what model should I use? Why are there so many models? What's the difference between all these models? And this being YouTube, I thought no better way to cover all the differences between common machine learning models than rank them in a tier list. And just a disclaimer, usually whenever you're actually doing this in practice, you want to do something more rigorous and systematic, something like doing cross-validation and hyperparameter tuning and grid search. And since there's always differences between the data, the task you have, the end target you're predicting, all these models, while there's some heuristics that could guide you in your choice, it often comes down to what just works best on your problem. And the only way to find that out is to actually run experiments with your data, with your task, and try out a bunch of different models, try out a bunch of different parameters. But, even though you should take everything with a grain of salt, you still can't have opinions. So without further ado, let's get into Jonathan's opinionated guide to machine learning models. All right, so for this tier list, there's hundreds, probably thousands of machine learning models. There's new ones coming out every day. So instead of saying of all the models out there, what is the best and which one do I like the best, I thought it appropriate to look to probably the most popular machine learning library, scikit-learn, since it's something of an agreed upon consensus of all the developers and core contributors of the library of this is kind of the essentials of doing machine learning. It doesn't have super experimental or research methods in it, yet it does have a wide enough breadth to cover most of what you might need to do with machine learning. So here I'm just on the scikit-learn docs page, and if we click in just to look at something like supervised learning and classification, mainly classification and regression, and not going through all of these, but most of what I'm going to go through is on this page here. So I'm not just going to be taking all of scikit-learn supervised learning and ranking them without much else commentary. So hopefully this will be a somewhat informative video. And I'm going to be ranking these or assessing these models based on the accuracy or how predictive is the model. Secondly, I'll look at performance from the computational perspective. Does it take a long time to train? Does it take a long time to give predictions? Third, I'll be looking at the overall complexity of the model kind of from two angles. One is the complexity of, is the model hard to implement? Is the model something that is kind of finicky when you're trying to debug it? Or is it something that usually works pretty well most of the time? And this comes into how do you tune the parameters? How do you tune the hyperparameters of the model? And all sorts of other things, which often, if you are a practicing data scientist or machine learner, probably takes up most of your time. And lastly, I'll just kind of touch on ideas of interpretability, or if you're an end user, how usable is this model? So if you haven't seen a tier list or have any idea what a tier list is, I was new to it except for a few months ago when I saw a video on them. You basically have these 7 different categories or rankings, S, A, B, C, D, E, and F. To kind of give you a sense, S is kind of the A plus, your most favorite. Sometimes you have multiple S tier items or whatever you're ranking, but often S tier is kind of reserved for the cream of the crop. F tier is kind of the analog for the worst. So F tier this is the absolute worst, and A, B, C, D, and E kind of fill in the gaps, with C being something of the neutral average. So, somewhat appropriately for the first model, and often the first model that folks learn, I want to rank linear regression. Now, linear regression is probably the most used model, both in machine learning and statistics. Now, there's a lot of nice things to like about it. I'm gonna actually rank this, I'm gonna put it in A tier. Not only is it the most commonly used, it is probably the most versatile model. People use linear regression in pretty much every field. In terms of all the other models we're going to look at, while it may not be the most predictive, it's often most useful for inferential statistics. ANOVA can actually be seen as a special case of linear regression. So linear regression can be used for anything you would use ANOVA for, things like experiment design and hypothesis tests. Linear regression trains fast. It's really easy to implement. in all sorts of environments, and it gives predictions lightning fast, since all you have to do is multiply your features by your parameters to get a prediction. All right, so next, I'm actually going to be doing two at once. I'm going to be looking at ridge and lasso regression, since they're both kind of different sides of the same coin. Ridge uses L2 regularization, Lasso uses L1 regularization, and both of these are basically extensions of linear regression. So I'm actually going to amend this and bump linear regression down to B, since usually when I think about linear regression, I often am thinking about ridge or lasso. And ridge and lasso are kind of just better extensions of the ordinary least squares. So for lasso, I'm going to put in A tier, and I'll put ridge in B tier. Lasso does have this really nice property of enforcing sparsity in its parameters. Now, people often use this somewhat erroneously to do things like feature selection, but there are these pathological cases where the features themselves may not actually be important in what Lasso selects. So you shouldn't treat the feature as being important, but if you just need fewer features, you can think of Lasso as selecting a subset of features. The weight of the parameter doesn't necessarily relate to the importance of the feature. And if you do need, for whatever reason, you have very high dimensional data and you want to compress that data space a little bit, you can use something like Lasso to train a model with far fewer parameters than maybe your thousands or hundreds of thousands of parameters you would have had otherwise if you kept your feature space pretty dense. All right, so coming up, I will say one of my favorites, logistic regression. Now, logistic regression, it's probably the model that, if you want to quantify it this way, has made the most money for companies. It's usually used for a ton of things in ad tech because of these nice properties of giving blazing fast predictions. So if you come to a web page and you need to serve an ad, you really only have a few tens or hundreds of milliseconds to give a prediction. So you need something blazingly fast that is still fairly accurate. Similar to linear regression, of all these models for classification, logistic regression is probably the only one that could be used in an inferential sense. So just like linear regression can be used to do things like hypothesis testing and used in experiment design for regression problems, you can do the same thing with logistic regression in a categorical problem. The other really nice thing about logistic regression is if you properly calibrate it, its probabilities that it gives as output are actually close to true probabilities. All right, up next is my favorite. We have naive Bayes here. And I'm going to put this in S tier just because I'll explain why I'm putting it in S tier. It may not be the most commonly used. It may not be the best at any one thing, but I often think of naive Bayes almost as being second best for everything. It actually trains blazingly fast. You can implement it fairly easily in a large scale or distributed system, since most of the computation involved in training naive Bayes isn't some iterative procedure like gradient descent, but you just basically do a bunch of counts. So it naturally parallelizes really well. It gives predictions, probably the fastest of any model on here. So performance, it takes the cake on this one. Complexity, it's not a complex model. Again, super easy to implement in a distributed system, or even if you want to implement in something like SQL or a database. Usability too, in terms of kind of the complexity of it, there really isn't much to tune with naive Bayes. Of course, there are some things that you can kind of experiment when you are validating your model. Compared to something like a neural network or a support vector machine, naive Bayes is kind of set it and forget it, and it performs really well. And one of my favorite quotes that I don't remember where it actually came from, I think it's from a paper or a textbook, is, "It's not amazing that it works so well, it's amazing that it works at all." And I really like that ethos of naive Bayes. Now, a little asterisk on naive Bayes, even though it is S tier, I will say that, again, since it is kind of second best at a lot of things, usually there's another model that better fits your use case, since you choose your model for your use case. If you had to pick a single model that you need to use all the time, if you're going to a desert island, you only get one machine learning model to do whatever you need to do, I would probably pick naive Bayes or something like random forest. But given that's not how machine learning or data science works, Usually when you are doing something like cross-validation and experimenting with all these, usually there's another model that does better, but in terms of one model that does good enough across a lot of cases, I'll put my money on naive Bayes. All right, another kind of one of my favorites just because it's so simple. We have k-nearest neighbors here, and I'm putting this in C tier. It's probably something that I wouldn't really ever use, but I appreciate the method itself. It's the only model here that actually doesn't have any training process. The way that it works, all of the computation happens when you give a prediction, but since that's usually where you need to make things faster, it's kind of this funny inversion. You don't have to train it, which is cool, but usually you can train things offline and you have all the time in the world to train your model. It's when you need to give a prediction that you want the prediction to happen blazingly fast. But with k-nearest neighbor, it can take a very long time to actually give a prediction, since you have to look at, in theory, all of the data points for a new prediction you're going to give. Up next, we have a 90s favorite, the support vector machine. So support vector machine is kind of this really nice, mathematically elegant and beautiful solution. It's this maximum margin classifier. If you can see on this image here, it says, what line can I draw through my feature space that maximally separates both of these classes? So it, in theory, gives you something of this idealized decision boundary. I'm actually, since I need or I want to put one in F, let's actually bump it up to E, since if I was doing this 10 years ago, I would probably say support vector machine is the most predictive model you have out there. It kind of was what people use really complex models like neural networks now for, that before deep learning. The reason I'm putting in E is it's notoriously hard to train. There's a bunch of hyperparameters that really, the model can be super sensitive to the hyperparameters. So not only does it take a long time to train, it takes a long time to tune because you have to do a bunch of these validation, training, and evaluation cycles. It does give predictions fairly fast, which is good, but it can be a pretty complex model and nuanced to implement and debug. Of all the models we're going to look at, it is one of the more predictive ones, which brings us to decision tree. I'm probably going to get some flack. I'll put decision tree in D. I would say the only nice thing and the only thing to use a decision tree for is its interpretability, but even though it kind of has this reputation of being the most interpretable model, if you use it for anything that has any non-trivial number of features, if you have more than 4 or 5 features, usually the splits in the depth of the tree make it somewhat hard to interpret. If you're using this for any practical or real-world data set, I would say it's rare that you have less than 10 or even less than 50 features a lot of times. So if you do have any sort of dimensionality to your data, this decision tree is going to be equally as uninterpretable as something like a SVM or neural network. I did put it in D though, because it's a pretty important component for the other tree-based and ensemble methods. So here, this picture of a forest, let's say this is random forest or just generally a bagged ensemble. It's kind of my go-to starting model. If I have no idea about what would work, or if I haven't explored my data, it does have the really nice and somewhat unique feature of actually giving you somewhat real feature importances. So while people try to use Lasso to do things like feature selection, you can with a random forest, since you have this ensemble of a bunch of decision trees giving predictions, get some sense of how important given features are. Random forests are probably one of the most usable, up there with naive Bayes. It's usually much more predictive than something like naive Bayes. So you have a lot of the niceties of reasonable performance. It can take a while to train, but once you've trained it, it can give pretty lightning fast predictions. It does have maybe not the best, but the second best predictive power. And in terms of interpretability, it does give you the sense of which features are important for your given problem or task at hand. What I'll say is a cousin to random forest is gradient boosting. Now I'm actually going to put gradient boosting, and in this case specifically XGBoost, in S tier. Woo! Since it is kind of this all-star of machine learning models, it's probably the model that's won the most Kaggle competitions. So if you're looking at just raw predictive power, XGBoost is kind of the top of the top. So you get the most predictive power. You do get all of the other nice features of random forest. You can get some sense of feature importances. Another nice and clever thing with XGBoost is you can implement it blazingly fast, either on a single machine. You can do out-of-core learning or implement it in a distributed system. It's kind of one of these almost magical models in the sense that it does a lot of clever tricks. It has crazy wide support across a bunch of different programming languages, libraries, environments that you would do machine learning in. It's the Michael Jordan of the machine learning modeling world. All right, you can see an interesting distribution here, even with the list so far, is that I do have a fairly high opinion of a lot of these. So again, they're all skewed kind of towards the top here. But, you know, a lot of these, again, being common algorithms that have usually stood the test of time, means that they are good and good for some use case, regardless. So by nature of being in something like scikit-learn, chances are these aren't useless models or methods. We're getting to the end. This is the penultimate model. And for this one, I'm going to say neural networks and deep learning. I'll group them in one. I'll put this actually in A tier. I want to put it in S tier just because the cool, crazy things you can do with deep learning. And yeah, let's put it in S tier just because, not because it's been hyped up and it gives maybe the best predictive power. It can be really hard to train and tune. It does have a lot of bad things about it, but I would say S tier just because of the cool things you can do and the cool art you can make with it. So here is Google's experiments or AI experiments. Most of these probably use some form of a neural network. You have things where you can basically either identify drawings or make drawings yourself. They can be generative. You can generate music, text, as well as enable a lot of really awesome accessibility technologies. So I will say deep learning, I'll put it in S tier, mainly because of the things you can do with it. In terms of neural networks or a deep neural network as a model, I actually probably would put it maybe lower in A or B, but in terms of the uses for deep learning and neural networks, I'll say S tier. So model-wise, I'll probably say XGBoost, S tier model. Application-wise, XGBoost, I mean, you can kind of use it for anything to give predictions. Neural networks and deep learning, cool shit you can do with it, definitely S tier. In terms of the model itself and just neural networks in general, I'll say maybe A or B tier. Which brings us to, now I'm not saving the best for last, but I am saving a cool model for last. So the last one here is Gaussian processes. Now Gaussian processes can be used for classification or regression. They're maybe more often used for regression. And I'll say Gaussian processes, I'll put them in B tier. They're kind of not a new model, but they're a model that's newly being recognized. So a lot of people in industry, I know Uber does a lot of stuff with Gaussian processes. They are getting attention because they are these very flexible models, and there's actually a bunch of papers and research that show the equivalence of a Gaussian process and a certain type of neural network. An infinitely wide neural network can be shown to be equivalent to a Gaussian process. From a usability standpoint, Gaussian processes are pretty great because they give you these confidence or probability bounds on the prediction. So Gaussian processes are what's often probably the most commonly used model inside of things like Bayesian optimization or Bayesian hyperparameter optimization. And while they may not be the most useful across the widest range of applications, they can do very useful but very specific things. And the theory behind Gaussian processes is really interesting in that they're these Bayesian nonparametrics. So nonparametrics aren't no parameters, but rather an infinite number of parameters, which makes it very flexible. And since it's Bayesian, you get these probability bounds on the predictions. So with that, I'll end the tier list with Gaussian processes, put it in B. Now, before we go, I'd like to thank the sponsor of this video, Jonathan Industries. Now, if you don't know about Jonathan Industries is the leading producer and manufacturer of Jonathans in the world. I'll link to Jonathan Industries in the description. If you're in the market for a new Jonathan, definitely I'd recommend them. If you liked the video, go ahead and subscribe. If you think I was wrong in my rankings, if you hated this video, go ahead and smash that like button anyways. And leave a comment telling me how wrong I am.